going to record. Again, welcome to MENG 260 and another Zoom session. Today is Thursday, June 11th. Okay. Welcome all of you. Hope everything is going well for you. And so I was talking about, the rules for, not for my class, for all your classes, my friend, okay? Because I'm a director of engineering at Mesa College. I build the engineering program from scratch, okay? I have been at UST since 1994. So every single semester, and I've taught every single courses that took when we started mechanical engineering, when we had electrical engineering to begin with back in 80, they started in 1988, and then I came in 1994. But anyway, so all I wanted you to know that I'm here to help you, but please try not to go, just say I did. Okay. You understand what I'm saying, okay? All right. But to go over each single problem, this is what I run into. Someone, for example, problem number 1, and instead of problem number 1, you start with problem number 5. And then the sheet of paper, instead of being vertical, it's horizontal. And I have to go back and rotate it. That is a time. It takes time. Okay, all right, so please be careful. When you take pictures, make sure that your work is clear. So when I'm not able to read your work, you lose point because I don't know what you're saying. And also, my friend, let me just tell you one point in thermodynamics. Some of you are still not clear on this concept. If we are dealing with ideal gases, you apply the ideal gas law. Do not apply the ideal gas law to a liquid because it won't work. So you need to go to find the enthalpy or the internal energy based on given temperature and pressure. You need to use the tables, proper tables, to get those enthalpy. For example, if it's in a saturated liquid, then you have H subscript F, H subscript G. If it's a V, a specific volume, V subscript F, and V subscript G, and UF and UG, okay? Do not mix up the U with V, little v, okay? I saw that on the exam that somebody just using U as V and V as U. Now, you got the point that please do not mix up the two things, okay? So fluid, liquid versus gases, whether we have monoatomic gases or diatomic gases. Remember, when the temperature increases, that approximation formula that I have explained called CV, specifically the constant volume for say for closed system, CV, which we said for monoatomic gas, that is 3/2 times R. But my friend, there are two types of R. R is a gas constant, and we have universal gas constant. So gas constant R is equal to universal gas constant R bar divided by molecular weight of that gas. So that is maybe a better way to determine the R, okay? R. CV, also you need to use the table in case that, you don't want to just do the approximation because it will be error, there will be error. Try to use the table because we have a table for a specific volume and a specific heat at constant volume, a specific heat at constant pressure. Because CP works with the enthalpy. CV works with internal energy, okay, CV. So I am going to post, okay, my friend, just be patient. I am redoing, it took me like 2-3 hours to write clear, neat as possible so I could just post the solution to exam 1 on Blackboard so that you can look at the solution and look at your work to see if I was fair giving you the points or not, okay? All right, so first do that, and then if you have any question, I'll be happy to help you out, okay? But if 37 students email me, ask me, can you go over my exam one by one? That we need another semester to do that, okay? I believe me, I gave you law of partial credit, okay? Law of partial credit. So just be patient. This afternoon, I will post the solution to exam one, okay? Another announcement. Some of your students, some of your classmates asked me to postpone the homework to maybe tomorrow, okay? I said, no problem, because there's a lot of stuff's going on, and you can, some of you have already submitted homework number 4, okay? And I'm going to assign homework number 5 on chapter 7 and chapter 12. And then we're gonna have exam on Monday on chapter 5, 6, 7, possibly 7, not 12, okay? It will be too much if I go to 12. So 3 chapters for midterm. And then we have final exam will include the chapter 12, which is the fluid mechanics. And also I need to cover the portion of fluid mechanics that is called internal flow and external flow and other chapters, okay? I'll let you know what that chapter is. And plus I have to cover heat transfer, conduction, convection, and radiation. It just is required, it says it's required. I wish this was a semester course. I will have more freedom to do that. But we know that the situation, okay? So let me tell you this. I will talk about the exam tomorrow, okay? Tomorrow. Again, homework number 4, you can submit by tomorrow, Friday evening, before 10 p.m. That will be fine. Okay, so this way you will learn more, okay? You will learn more by doing the homework. Those are the good problems on the homework, okay? Good problems. All right, so that's what I wanted to share with you. I think I covered a little bit of everything I needed to cover, okay? All right, so, and then I know that some of you just like to email, one after another. I try my best to reply back to you, okay? I try my best. Again, about the exam, because you guys, I think everything goes well until we have exams. Then we have entropy, everyone, okay? So this is not the first time, a million times I've taught classes, okay? All right, so, but just be patient. I have great understanding of psychology of the teaching and human behaviors of what's going on, okay? All right, so not only a teacher, I'm a very good politician, very good, psychologist, and a good person, okay? Yes, first of all, knowledge is great, good to have knowledge, but you have to be a good human being, okay? Then the knowledge is going to help you to excel, to go to the next level. So that's my advice to you guys in life, okay? Life. Teamwork, being PR, good public relation, and connections, being able to connect with other people so you can move along the path in a smooth way, okay? So, all right, my friend. And then after this lecture, I will be available to answer any questions you have. Please hang in there, and I will be happy to respond to any questions. Okay, all right, so is that clear? All right, chapter 7. Remember in chapter 6, we talked about the entropy for cycles, like a heat pump, refrigeration cycle, Carnot cycles, and all that. So chapter 7, we're gonna just touch base on another level of entropy, because second law of thermodynamics, for reversible process, we said Carnot engine is the good example of reversible cycle, reversible process, okay? It has a reversible process. Now, we have also entropy that deals with the system versus cycles, okay? We're gonna see what's going on. Entropy rate balance. Entropy, like enthalpy and internal energy also, it's a thermodynamics properties that for ideal gas, you can apply, the ideal gas law. But if it's a liquid, make sure you use the table. Otherwise, your result will be way off. Okay, all right. So entropy rate balance for control volume, and this is the change in entropy for control volume, or the rate of entropy change for control volume is equal to sum of all the heat transfer rate over temperature. That's the language of entropy, okay? Q over T, or Q dot over T. It's a heat transfer rate over temperature. And it depends on, the amount of energy that is entering the system. It's a summation, but we just, have one goes in, one goes out, okay, in and out. All right, so, but it's a summation here, no problem. That's the rules. It's a mathematics also, the language summation, notation, and math. And then J means, the first rate, second rate, third rate, and so on. So, and also we have rates of entropy transfer, okay, M dot ISI minus this rate of entropy. And this is the production, the rates of entropy transfer in and out of the system, okay, system. We're not talking about cycles, system. So this sigma dot, it's just a strength of the system that we have, or the rate of entropy production, okay, sigma dot C. In most cases, we just neglect that, or we say we don't need to deal with the rate of entropy production, okay? And we can always simplify the governing equations, the original equations, with the simplified equation, and you will see that it's based on assumptions that we make, because some terms, because it's the amount, the value of each term, like a potential energy or sometimes kinetic energy or inlet velocity, is very, very insignificant compared to exit velocity in the case of nozzle. So, and this is the balance for control, entropy rate balance, okay? And there we go. At the end of this section, you should be able to describe how the Bernoulli equations, okay? So that's what for entropy, and I'm gonna have some notes. I'm gonna talk about entropy, okay? So that is, for time being, that's what we have, the entropy rate balance. The next part, we're gonna talk about the fluid flow, okay? Chapter 7, chapter 12. At the end of this section, you should be able to describe how the Bernoulli equation is a simplification of the mechanical energy equation, which is powerful equation, okay? Powerful equation, Bernoulli. And we're gonna talk about compressible flow versus incompressible flow, and then dealing with the density. Remember, my friend, density is inverse, it has an inverse relationship with a specific volume, okay? Rho equals 1 over a specific volume, or a specific volume is equal to 1 over rho. Rho is a density. For gases or for liquid, you need to look that up in the table, or they will provide you on the test. They say the density for water is this, density for air is this. Okay, all right, so applying the Bernoulli equation to internally reversible fluid flow problem, apply the mechanical energy equation to determine losses in turbines and pumps. Okay, sometimes in Bernoulli equation, we try to just remove the term for the turbine and a pump because it may not be included in the system. Okay, we're dealing with the system. All right, so Bernoulli equations assume internally reversible means no friction, okay, no friction in viscid flow. No mechanical devices like turbine pumps in the control volume, okay, for the Bernoulli. So the energy in the, okay, so this is the beautiful general form of a Bernoulli. But Bernoulli is going to be, equation will be simplified to a very compact form called delta P equals 1/2 rho V squared, which we call it the difference between the stagnation pressure and the static pressure. That we're going to measure that by using a U-tube manometers, or we use the pitot tube that we insert that in an air duct, and then we can measure the differential pressure also. Okay. So, all right, so, and that is, they call it 1/2 rho V squared. We call it dynamic head. So we're going to be talking about the head loss in fluid mechanics, head loss, velocity head, potential head, velocity head, pressure head, and so on. So each term has a units of pressure on here on Bernoulli equation. These are all pressure, maybe it's a Pascal or PSI. Okay. Each term has a unit of pressure, a specific weight, gamma. Okay, my friend, this is, we use this a lot in fluid mechanics. Gamma equals rho G. Unfortunately, in fluid, we use the symbol Q. The capital letter Q is not a heat transfer, it's a volume flow rate. That when you switch from one concept to another concept, or from thermal to fluid, And then some of the terminology is going to be confusing because we have been using Q to represent the heat transfer. So then we say Q equals the volume flow rate. But I will just repeat that so you don't forget. So weight per, so gamma is also can be written as G over V, a specific volume, because rho equals 1 over V. All right. Then we go to mechanical energy equation. These are the fundamental equation for mechanical energy and Bernoulli equation. And mechanical energy accounts for irreversibilities associated with turbines, pumps. Okay, now we're going to include the turbine and pump and the head losses. We have a concept, and design concept that when we are designing pipes, okay, we have a pipe that we wanted to transfer fluid from one location to another location, or it has elevation. So we need to have a powerful pump, and also turbines and compressor and all that. So losses are two types. We call it major losses and minor losses. Minor losses due to friction and some maybe due to the bend, elbow, or some contractions, and so on. Okay, so we will discuss that as we go through this concept of mechanical energy equation. So we're going to enter this area that we call it the head losses. Okay, head losses could be minor, could be major. Okay, or it's if there is no, for internal flow, if there is no friction, assume it's frictionless, then there is no, minor losses. Okay, so accounts for work at crossing the control volume boundaries. Okay, accounts for work crossing the control work, because here we have a power per unit and mass, so that could be the power due to turbine and pump and so on. So initial pressure over a specific rate, because that will convert this to units of length, because each term on the left-hand side and on the right-hand side, if you balance the units, you end up with each term, we call it the length, okay, units of length, because head losses has a unit of length. So that's a general formula, okay, and it can be simplified to reduce to a more compact formula for energy equation. All right, so internally reversible processes. First law, closed system. In del, I call it del, in calculus we call it the partial derivatives. Del or d for just the derivative change of velocity with respect to time, or we say dy dx, okay? Or we have the acceleration equals dv dt, change in velocity with respect to time, position dx dt with change in position with respect to time, we call it velocity, and so on. Okay, so del. Q, again, this is not a volume flow rate, this is just still we're talking about heat transfer. Internal reversible, and then change in internal energy. Sometimes we say that del W is, and it's a small amount, okay, a small amount of work, a small amount of a Q leaving or entering the system. And for internally reversible process, okay. All right, so this is equivalent to PVV, okay, PVV, pressure change in volume. And the second law of thermodynamics says that ds equals, this is the powerful formula in entropy, del Q over T, or del Q, internal for internal reversible, it equals a temperature, the product of temperature and change in entropy. Okay, so you watch for that because you will be using it in maybe homework problems. Okay, right? So, and then this is the first law is going to simplify. Okay, simplify to change in entropy times T. Okay, because this is what a Q, correct? The first law of thermodynamics said Q, the amount of heat transfer into the system, is equal to the change of internal energy plus the amount of work. If it's the work is done by the system, it's positive. If the work is done on the system, we say negative. Okay, but this is okay because if you go back to the fundamental of first law of thermodynamics, we said change in internal energy is equals to Q minus W, right? But if you rearrange it, and then Q, which is this is TDS, okay, TDS. If we just remove this del and we say Q equals TDS, so we substitute it here, and DU is right there, and then PDV for this one. Okay, so that's a very nice formula. Now we are entering the area of entropy, because now we have to go to, for example, for fluid or liquid. Now we need to find the entropy, whether it is SF or SG, and S1, S2. So first law of the thermodynamics also is introducing that. H, capital letter H, total enthalpy equals total internal energy by definition plus the work. Work is a PV. Okay. So if I change in enthalpy equals a change in internal energy equals a change of PV for the work, VDU plus VDP, okay, VDP plus PDV, okay, it's like having a product rules and derivatives, right? Okay. dP, or we say VDP plus PDV. Now what do we have in here? DU plus DU plus PDV, okay, DU plus PDV is equals to DH, okay, DH minus VDP. So you rearrange all that, okay, here, and then you end up with this, okay? Just a simple basic rearrangement of the equation, okay? So, so that's the problem we have here. And then, so there will be a situation that you need to use this formula here. And then TDS, because DU means DH minus VDP, okay? DU equals DH minus VDP. So we substitute in here, okay, TDS, right? So going through this a little bit of simplification. So now we can write the TDS, temperature change in entropy, and instead of having the internal energy plus PDV, we have change in enthalpy minus VDP. Okay, you see how it's different? Because in H is always think of H as open system, U as a closed system, piston cylinder. And then when you have the piston, for example, is moved out, then you have a portion of the process, we call it open system process, okay, open system. Open system process in the ideal gas law, DH equals MCP delta T, MCP delta T for internal energy for closed system, we say MCV delta T, okay, MCV. And CV means a specific heat at constant volume, CP a specific heat at constant pressure. All right, I need to have a little bit of water. I think I got, sorry about that. All right, so, so this is a TDS equation. All right, so, and then we have internally reversible process, control volume entropy rate balance, okay, Q dot CV over T. So that's the entropy, correct? That's entropy. And then, I'm sorry, the rate of change of heat flow and control volume over T, plus the M dot S1 minus S2, which is change in entropy, plus the strength of the system, okay, sigma dot CV. It looks like a stress, okay, a stress. All right, so this part, in most cases, they just set it to 0, okay? All right, so then we have the Q dot CV and dot internal reversible, like a Carnot engine, and T equals to T S, because we cross multiply and bring the M dot underneath the Q dot CV and dot, and then equals T ST minus S1, and that is also the good definition of the entropy, okay? And is equals to, and this is also equal to 1 to 2, because entropy is independent of path, so that it can go from 1 to 2, or maybe it goes in different direction, because the entropy is disorder. Okay, all right, so independent of path. So the limit of integrals, and TDS, we can always, this integrand here, we can replace it with DH minus VDP. Now we are talking about the a specific, right? A specific entropy and specific enthalpy and a specific volume, and times the change in pressure, VdP. So when we do that, assuming fluid is incompressible, okay? Incompressible. This is very important. Like, remember I talked about the compressive ideal gas law versus non-ideal gas law. Now we have to be very careful about the compressibility of the material versus incompressible, okay? Let me see, someone, I think it's a chat, okay, in the chat. Perfect, can we go over an example? Yeah, definitely, I will go over example on how to use this, okay, RSO. If I don't have time to go over today, but tomorrow for sure, I will prepare number of example problems to be able to apply or utilize these formulas in application problems, okay, RSO. Always the theory, we have to deal with the theory, and then we go on and look at an example problem, application problem. So anyway, so this is the situation that we have. We call it a incompressible versus compressible. Okay, please pay attention to that. You get, because of when the fluid is compressible, that means the density will change. Okay, density will change. But if you incompressible, like water, you cannot compress the water so that the density doesn't change, correct? From left to the right, okay? But if we have an m dot rho 1 v1, m dot rho 1 rho 1 v1 velocity, and density of the left side equals to m dot or m dot 2 rho 2 v2. If it's a incompressible fluid, then rho dot 1 equals rho dot 2 equals rho. Okay, you can say equals rho. Okay, so here. Then control volume energy, again, energy equation. We have the Q dot CV m dot minus W dot CV m dot for internal reversible, change in enthalpy, change in kinetic energy, and change in potential energy. Okay, change in potential energy. And Z, we call it elevation also, okay? And G is gravitational acceleration. So Q dot CV m dot, okay, all right, so that again, in this formula, you might just have, you might remove this W dot CV m dot, or you might remove this one, it's set it to 0, and then there might be the question as to find the velocity, V2, and V1 is given. So, and then you might just neglect the G Z1 minus Z2, then all this equation is going to end up with this, the enthalpy and the kinetic energy. Okay. So, and Bernoulli equation, okay? And Bernoulli equation, so control volume energy, the change in enthalpy, and then we plug the number or the terms, and then we have we solve for W dot CV m dot. This part and this part will cancel each other out, and then we have minus VP2 minus P1, and then we have a VP work, and then kinetic energy, and then we have GZ1 minus Z2. So in an application problem, you have the governing equation, but you can simplify it to fit that application problem. Okay. All right. So rearrange it. Ideal process is internally reversible, and then we have P1 V1. We put it on the left-hand side, plus V1 is square over 2 plus GZ1, because eventually this is going to lead to a Bernoulli equation, and then we can simplify the Bernoulli equation to a simplest form called change in pressure, or change in pressure difference between the stagnation and static pressure equals to 1/2 rho V squared, which is the dynamic head versus the difference of differential pressure. Okay. That we can use a U-tube manometer assembly trying to measure the difference in pressure, or we have a direct measure because delta P equals 1/2 rho V squared. If we know the velocity, we can find the delta P because rho is constant. Okay, all right, so mechanical energy out, mechanical energy in, and then internal reversible fluid, no control volume works. So then we have this simplified version, and I think it's almost the same P2V, V2 is 4, and then they just get rid of this part here. So we have a, and also we're going to divide everything by V, specific volume, and we end up with this here. And then if I bring this P1 minus P2, and then I have 1/2 rho V squared, and that will end up to be Bernoulli equation simplified. So ideal process internal reversible, the same thing. Okay, we're getting to this, same formula is repeated. The specific weight is rho G, so we're going to be dealing with that. And mechanical energy, again, we're repeating the same thing. Okay, same thing. So now we have a W dot CV. It could be the turbine, it could be the pump, the power of the turbine, power of the pump. And then the head, the turbine HT means turbine head is this here, and the head for the pump is this equation here, which is W dot P for the pump divided by M dot LG. Okay. I'm going to give you a homework problem that you will be utilizing this formula, and I'm going to go over the example problems tomorrow. Okay, so this part is done. Okay, just hang in there, okay? Hang in there. I have some notes to go over. Sometimes when I don't like the PowerPoint because it's sometimes boring to go over PowerPoint, even in the classroom, when I'm in the classroom. So let me stop the share, and I'm gonna post this for you on Blackboard, okay? So far I have been good. I've been following all this promise that I've promised to do certain things. So just be patient, I'll get there, okay? If I stop the share, and then I can go to, where should I go? I have to go to here. I have to switch a little bit, okay? So, no, okay. And now I need to go to that. Okay, I don't need to share now. I have the direct light for the dock camera. Okay, now I have to be very careful how this will work. Okay, so just pay attention to this, okay? Let me just enlarge it a little bit. Okay, do you see this, my friend? Can you, is that visible? Yes?
Yeah, you
okay.
See the top half, yeah.
Yeah, is that good, Matt? Okay.
Yeah.
All right, so, back in the 80s, we used to use the transparencies or the plastic, and we had the overhead projector, and this was all the heat was generating, and I was giving a presentation in the summertime, and I was sweating in front of, the whole people trying to explain a research paper that I've done. I was trying to prove my case. And then I was using those little plastics, the plastic you put. Listen, I'm talking about you guys were not born about 100 years ago. And now when I just go back to this now with a dock camera, it's much better. This technology is much better compared to overhead projector that we used to use, the old machine with the light is coming down on it. Okay, all right. So we have a volumetric flow rate. Again, some people call V dot, which is a volumetric flow rate. Okay, my friend. Area times velocity, okay? That's not a specific volume, it's velocity. So meter squared times meter per second is a cubic meter per second. That's a volume flow rate. In a flow design of volumetric, we call it volumetric flow rate. And some, people that are in the application problems or air conditioning design or some other design, and they wanted to explain the flow rate. They call it mass flow rate or volumetric flow rate, okay? Volumetric flow rate, in our textbook, they use Q, okay? Q, capital letter Q to represent volumetric flow rate. But another textbook, they use V dot, total volume. M dot is a mass flow rate, which is the total volume rate over a specific volume, because that is also what do we call that? We call it the 1 over rho, okay? 1 over rho, 1 over density. So since the specific volume is a 1 over rho, so volumetric flow rate is area times velocity over a specific volume. This is confusing between this symbol here and here, and that is a meter cube per kilogram per meter cube. And then we can just replace the V with the 1 over rho, so we're going to have rho AV. So you will see this over and over, this formula here, okay? M dot equals rho AV. And again, if it's a compressible fluid, then the density changes. If we have a rho 1 A1 V1 equals rho 2 A2 V2, and they ask you to solve for the inlet or the exit area or exit diameter for the pipe that you have, or the nozzles you have, or diffusers you have, or you have a tank that you have the pressure and then inlet pressure, and then you have an exit pressure, and you have a reduction in area. So they want you to calculate either the diameter, exit diameter, inlet diameter, and the area, inlet or exit. Okay. So conservation of mass, sum of the m dot in equals sum of the m dot out. It's just like I'm trying to review this for you. Okay, review. Okay. Again, first law of thermodynamics. We have Q12 minus W12 is equal for liquid, okay? For liquid, we don't use the ideal gas law, so it will be, because this is a specific internal energy, that's why we always have M attached to that, correct? Because the total internal energy is defined as, or the specific internal energy is defined as total internal energy divided by mass. So when you rearrange that, because this is equivalent to delta U, a big U, okay, large capital letter U. So if we replace that with MU2 minus U1, that means we're talking about a specific internal energy that you can look that up in the table for the given intensive properties, okay. Q.1, and then also this side here for the closed system, that's nice. And then if we have an open system, then we have in terms of rate, heat transfer rate and rate of work done by the system or on the system equals to sum of the m dot out h out. That's an enthalpy, right? And then this is the m dot in h in. So these two, you have to differentiate between these two of first law of thermodynamics, with having the internal energy specific and specific enthalpy. Okay. Otherwise, the total enthalpy is denoted by capital letter H. And then if you have an adiabatic system, okay, if you have an adiabatic system, we have the Q is 0, so W dot is going to be, you'll rearrange this here, okay? So we're going to have F for control volume. So we have M dot N, okay, because there's a minus in here. So we distribute the negative to the right side also. The times -1, so we have a positive W dot and equals to M minus M dot out H out and plus M dot in H in. So that's a simplification. So internally reversible steady state flow, second law of thermodynamics, and W, and then this is reversible process systems and surrounding can be restored to initial state, okay, reversible process. So you apply the load and then you remove the load, the materials will return to its original position. We call it reversible process. W dot for state 1 to 2 minus MV P2 minus P1. Okay. Internal reversible steady state flow. Heat exchangers or nozzle, work is 0. Knowing heat and applying the first law, that's the formula we use. And then determine entropy, to determine entropy using the second law. Okay, this is where I wanted to get into. Okay, you will have a homework problem that you will be using this formula here for ideal gas. Okay, for ideal gas, this is the change in entropy. For closed system, we have CV, natural log of T2 or 2 plus the gas constant, which is the ratio of R bar universal. So gas constant divided by molecular weight and times natural log of the ratio of a specific volume over 2 over a specific volume 1. So for open system, we use the change in entropy to calculate the change in entropy for ideal gases. It's CP. You can look that up, okay? You can go to a table, you can find the CV for the given temperature or pressure, and you can determine the CV and CP, okay, CP. It's tabulated, okay? It's a table. and I'm showing you on a solution to the exam one, I'm showing you how to, which tables to go to find the CV, but we haven't touched based on CP yet. So we're going to be dealing with CP for open system. That means, also an enthalpy situation for if we are dealing with a liquid, then we have to use CP instead of CV for open system. So, and that's a formula here. And hopefully, that's just a review. Okay? And one more here, this basic review here, the second law of thermodynamics. The energy of an isolated system never decreases, okay? Entropy, okay? Entropy. The entropy of an isolated system never decreases. Okay? It either remains constant, reversible process, or increases in irreversible process. So we have, we had heat to equilibrium, temperature. We're going to raise the temperature, so we have increase in entropy. Okay, the entropy is going to be increased by having an external source. Okay, adding the external source or heat. So the total entropy of any system and that of the surrounding always increases. So remember the increase. So that is the a little bit of a theory behind the entropy, and that is one more part of the second law of thermodynamics, because I really wanted to share this information with you before I go to chapter 12. Maybe possibly tomorrow I can finish chapter 12. Okay, all right. So here maybe there was a portion of chapter 6 which we said reversible process if both the system and surrounding can be returned to their initial state. Irreversible means if both the system and surrounding cannot be returned to their initial state. That's irreversible. And then we already talked about the second law of thermodynamics using the cycle, the thermal efficiency. You guys are very good at that. Okay, you know how to calculate thermal efficiency and coefficient of performance of the cycles in chapter 6. Okay, that deals with also we call it the second law of thermodynamics. And then another part of the entropy, the general formula, the laws, and the physicists and the engineers like to talk about the change in entropy, which is a Q over temperature when we have a constant temperature. But when we have non-constant temperature, then ds, we have a differential, differential entropy, and instead of delta S, we use ds, dq, dt for non-constant temperature. So delta S is the integrals of ds, okay? Delta S is integrals of ds from A to B, limit of integrals. And then we substitute for ds, dq, dt. And what this is saying, it says entropy is a state variable. Delta S is pathway independent. So it can be directed in any direction, can be directed in any direction. For an isolated system of two objects, the transport of energy from object at high temperature, that we're dealing with a cycle, correct? Thermodynamic cycle. So for an isolated system of two objects, means hot reservoir and a cold reservoir, the transport of energy from object at TH, high temperature, to the object at low temperature, increases the total energy. It increases the total energy of the system. Say if we have a high state 1 and a state 2 to the low, heat begins to flow, and then number 2, object eventually comes to thermal equilibrium, where the new temperature, we call it the final temperature, okay? So delta S equals delta S at a high temperature plus delta S at low temperature. And then we can rewrite this as minus Q over TH for the total temperature, which is where the new temperature, we call it the total temperature, and then plus the QT, the low reservoir or a cold reservoir. This result is always greater than 0, and that is something that you will be maybe seeing this if you are doing research and you wanted to prove a formula that it deals with the second law of thermodynamics, the mathematician or physicist and people that are heavily involved in thermal sciences, they like to explain the laws of entropy. They are passionate about, they have a passion about the second law of thermodynamics. Then they go over this in details, okay? But since this is just an introduction to thermal sciences, I want to touch base on pieces here and pieces there, have a overall knowledge of what thermal science is all about, okay? If you wanted to learn more, then you take more courses in the area of thermodynamics, fluid mechanics, heat transfer, or alternative energy systems design, or there's a course that I remember I taught the course called HVAC, heating, ventilation, and air conditioning, and the solar energy, and so on. Okay, that's the area of thermal, or we call it the thermal sciences. Okay, all right. So, any questions, guys? I think that will be good enough for time being here. All right. All right. So let me see if I can bring this back in here. All right. Abbas, you look good on this picture, and you're smiling, correct? Where are you? You are in maybe, I don't know, that's a nice picture. I see in the middle of my screen is a picture of Abbas, okay? Any questions? Okay, let me just see if I can go out of this here. Oops, you cannot minimize, okay. Can you see me or can you hear me? Yeah. Someone can confirm? Because I want to make sure that my microphone is working.
Yes.
Professor, I have a question.
We can hear both of you, yeah.
Okay, fantastic. Thank you. Thank you.
I got a question, Professor.
Yes, go ahead.
So the thing with Google Drive is whenever we share something with you, we don't need to share it again and again and again whenever we upload files to the folder. So for example, for homework 4, if I upload it to the Google Drive, do you want me to share it again with you? I did share the original folders again. So do you want me to share it again? Like every time I upload something?
Yeah, I have the same question.
Yeah, can you please do that, because I'm having a difficult times going back and finding that folder, okay?
Okay.
Can you please, this is taking me so much time trying to look for it. Can you please just send me a folder that has homework number 4, okay? And instead of sending it to that shared folder, because I'm having a tough time finding it. That is where the problem is, maybe. Yeah, please just, for homework number 4, just to share that, those chapter 5 and chapter 6 number of assignments that you have worked on, you just share that, okay? Email it to me again.
Okay, so whenever we upload something, we just share the thing we uploaded again. So you can get the notification in your email.
Then that's what I do. I go and look at the email to see who has, and it says homework number 4. And I have let me just go to my desktop here. Just be patient a little bit, and I can tell you what's going on my desktop here. Come on. I can just go quickly here and then go to my Gmail account. Okay, account. Come on. All right, so 1 second, okay? For example, I'm going to show that here. It says, Mubarak Al-Hamri, it says submission email. Please find my homework number 4 attached, and I can see it. It says HW4, so I can see that. Okay, all right. So then I have Al-Sabah. It says homework number 4, and then Matt. It says homework number 4, and so on. Okay, Abdul Mohsen and Munera. Let me see now. Okay, and then I have my, okay, okay, that's homework number 4. I can see that. Homework number 4 for Abdullah Reyes.
So you want us to send it through email rather than Google Drive? Like, do you prefer that?
No, when you are emailing it to me, so it's in a PDF, automatically is going to be in a Google Drive, in my Google Drive.
Oh, okay. I got
It
it.
comes to my Google Drive. So I know that if I'm not being able to open it, then I can go download. Then there's a zip file. And that zip file is, when I click on it, it's going to give me a folder, a yellow folder. Then that's how I can just open it and then look at the problems one at a time. Okay?
So, Professor, for the previous ones, because what I was doing with all my previous homeworks and quizzes is that I upload them to the Google Drive. Do you want me to resend it to you via email and
Yes,
like writing down every single one of them?
yes, please do that because um, I'm having a tough time going back and finding your drive, okay?
Okay.
That's where my problem is. And sorry, but I'm not
Just
used to
wanna-
this kind of environment. So let's just hang in there.
I just
And
want to make it easier for you. That's the thing. That's why
okay,
we're asking.
okay. Yeah, because I see that what I do is I have uh, 37 emails. So what I will do is for homework number 4, as soon as I grade them, I grade that individual's homework, and then I copy it to my folder, and then I delete them. It goes to the delete, to the trash, but I don't delete the trash because in case I want to go back to the email, I can find it. But
Okay.
and also I have a copy of it in my desktop folder for the homework number 4. So I have to ensure that I have your work in both in a, because if I don't delete them from my list, then I have hundreds of email, and you know that it's not easy to look at the hundreds of emails. Okay, all right, so
Yeah, I got it.
okay, you got it. Okay, please
Thank you.
send it. Email it to me, and it's in a form. I can see the red symbol. It's in a red in a tab. It's a PDF. I can see that there. Or if I click on, for example, I'm gonna click on the homework number 4 for Al Sabah. So homework number 4, and then here it says homework number 4. So I click on it. When I click on it, it goes to my drive. It's a Google Drive now, okay? So I can see the homework beautifully, homework number 4, and I can double click on it, and it's a screen, that large. I wish I could maybe I could show you, but fantastic, okay? All right, no problem. Please email it to me, PDF file, and then have problem like a step, like if it's a problem 5.1, don't say problem 5.20, 5.1, 5.26 first. So go in order because I have worked on each problem and I wanted to look at to see what, because I don't
Yeah.
remember everything, and it really takes time to grade homework and grade exam. So it makes it easier for me. Please be organized, and then I can put it away. Okay, all right, thank you. I think it's we are learning. I'm learning, you're learning, so we are all working together. All right.
Do you want us to do the same thing for exam number 1 or?
Yes, for exam number 1, I already got that. Only 3 students, for some reason, I could not really find an email associated with that individual. Okay, so but the other students, they email me and it's there. It says, the name, last name, exam, or exam 1. So I have a list of 30 some students, 32 students, 33 students, and I look at the right side, it says June 8th. June 8th. So I look at the June 8th and I got the list of students that they emailed me that exam 1. And then of course it's a PDF file, but when I open it it shows up in my Google Drive because it's a Gmail account. Okay, all right, so I think we got it, correct? For exam number 2, please email it to me, that folder for exam number 2. For homework number 5, I'm gonna post homework number 5, do the same thing. Because as soon as I graded the homework number 4, I will save it on a folder, so I will remove it from my inbox. I will remove it, and it goes into trash. But this is not a trash, okay? Just a temporary place, and it's not deleted. It's still there as a proof. Is there until I go and delete the trash or remove everything from the drive. Therefore, I have 2 places that I have your record. I have on folder I've created. And also I have, when I delete it from the inbox, it goes to trash. So I have two places to go back and search for your work. Okay, so. Okay.
Professor, they're talking about